Bismillahirrahmanirrahim. So over here we'll discuss the biostatistics that we covered this year, and we have basically three topics that we covered this year in the MSK module. So number one is the sample size calculation, this one. Then the second one is the t-test, and the third one is the chi-square test. So starting off from the first one, sample size calculation. So remember that whenever we'll be asked to calculate sample size, we'll either be asked to calculate it for estimation or for hypothesis testing. The question will go on to say that we are estimating or we are hypothesis testing, so you'll have to use different formulas in both of these cases. So once they ask you are estimating, you'll have to use the formula for estimating, and once they'll say that we are hypothesis testing, then you'll have to use the formula for hypothesis testing. So sample size calculation. So just to give you a brief overview, if we recall, there are two kinds of statistics: descriptive statistics and inferential statistics. In descriptive statistics, we covered it last year, so it's not relevant right now, but the thing which is of relevance currently is the inferential statistics. So in inferential statistics, we have a sample and we have a population. So basically the sample is out of that population, and using that sample we are actually trying to guess various aspects of the population, because we can't actually test everything on the population because it's too large. So we'll have to take a sample out of that population to be able to guess various things out of that population. So once we take out that sample should have an appropriate size so that we are able to guess the same different kind of variables of that population using that sample that we are taking out of that population. So if that sample is not of the appropriate size, if it's smaller, then our study won't be accurate, and if it's larger, then we'll be wasting our budget on a larger sample size, even though we could have done it with a smaller sample size. So that's why it's very important that we actually calculate what the sample size should be. So let's start. So we have a formula to calculate the sample size. Here it is. So, but note that this formula is only for the case of estimating. So if we look at some of the examples first, like this one, we see the word estimate. Then in this example we see the word estimate. In this example we see the word estimate. In this example we see the word estimate. So whenever we see the word estimate in the examples or in the questions in our exams, it definitely means that we'll have to use this formula. So if the word hypothesis testing is used or some indication is made towards that aspect of inferential statistics, we'll have to use another formula that we'll discuss later. So basically, once you see the word estimating in the question, you'll have to use this formula. So let's see the various aspects of this formula. What are the values? So all you have to do is to recognize what each and every symbol stands for. Then you'll simply have to plug in the values from the question and you'll get your answer. It's as simple as it gets. So n is the sample size. Then second one, z alpha by 2. So z alpha by 2 has to be calculated using various factors given in the question. So we'll come on to this aspect of the formula later on. But for now, just remember that z alpha by 2 is a separate variable and it needs to be calculated using various inputs from the formula from the question. Then so n is the sample size, z alpha by 2 gets calculated using various steps. We'll come to that later on. Then we have this thing sigma. So sigma denotes the standard deviation. So the question will go on to say that we have such and such standard deviation, and you'll simply have to plug in the value of that standard deviation into this formula to get an answer. Then there's a whole square, and then it's divided by d square. So what's d? Let's see. D is the bound on error or half width. So in other words, the estimate should be within d units of the population mean. The question will state that the estimate should be in this much units of the population mean, and that's the d value. So this thing might not be clear at this moment, but just give me a moment, then it will clear inshallah. So over here, let's see. The question said within 1 unit of its actual volume. So what's the d value? It becomes 1 over here. Okay. So the question states that within 0.2 of its actual value, and then the d value becomes 0.2. And then the question states within 5 milligrams per deciliter of the true mean, and the d square becomes 5 square. Then the question states within 1.5 years of its actual population mean, and then what we have as our d value over here is 1.5, and then we take a square. So that's how d value works. So over here, n is equal to z alpha by 2 into sigma, which is the standard deviation, whole square divided by d square. So okay, in case standard deviation sigma is not given in the question, then we calculate it using the formula below. Standard deviation, so we actually divide the range given in the question. So there's actually a value called range which might be given there in the question instead of standard deviation. Just divide that range by 4 and you'll have your value for standard deviation. Okay, so this is how we calculate z alpha by 2. This is given there in the notes, but we'll come to it later on. So for a while, just trust me and let's move on to the examples. So this is an example. If we wish to get to estimate the mean volume of oxygen uptake for population of joggers with a 95% confidence interval within 1 unit of its actual value mu, we compute the required sample size using the above formula. Assume S is equal to 4.8 from previous studies. Okay, so for 95% confidence interval, alpha is equal to 0.05, alpha by 2 is equal to 0.025. So this step, just ignore it for a moment. It is involved in calculation of z alpha by 2. For a moment, just leave it. Just recall the formula and just plug in the values. So n is equal to z alpha by 2 into sigma whole square divided by d square. So z alpha by 2 is calculated using a set of steps. It is a brief summary of those steps, but we'll cover it in detail. So just remember that z alpha by 2 for a confidence of 95% is 1.96. For a while, just remember it. So 1.96 is plugged in over here. Then we have the value of sigma. So sigma is 4.8 over here. S is also a symbol for standard deviation. So sigma is also a symbol for standard deviation. So we just simply put in the value of S, 4.8 whole square over here, and then we put in the value of 1 because here we have confidence interval within 1 unit of its actual value. So we discussed that D, which is the bound on error, is actually found out in the question in this way. So we simply plug in the values and calculate. Therefore, at least 89 measurements are required for the purpose of estimation. So let's see, once we calculate, we get the value of 88.51. So why round it off to the next number? Even if it was 88.0000001 or even 88.000000001 or 88.1 or 88.2, 88.3, 88.4, 5, 6, 7, and so on. In every case, we'll round it off to the next number because we can't reduce the size of the sample by 1, even if by normal rules of rounding off it had to be rounded off to 88. Still, we'll always round it off to the next number, and then we'll state that at least we need 89 measurements for the purpose of estimation. So now let's move on to another example. Same formula, z alpha by 2 sigma whole square divided by d square. So because we see the word estimate in the question, so z alpha by 2, again we have 95% confidence, so z alpha by 2 for 95% confidence is 1.96. We'll go on and see how it is calculated, but for a while just plug in the value 1.96, which corresponds to 95% confidence. Next up, we have the value of sigma, which is 0.5, because it's written over here, standard deviation of birth weight is 0.5. So it's sigma whole square divided by 0.2 square. Why 0.2? Because they say that within 0.2 of its actual value. So here we are, 24.01, as I mentioned before. We'll always round it off to the next number, never the previous number. So therefore in this case the sample size at least 25 is required. Okay, so all examples which are going to follow are similar. So now let's move on to hypothesis testing. So similar to estimation, we have another formula for hypothesis testing, and let's see what that formula looks like. So here is a formula for hypothesis testing, and here is another formula for hypothesis testing. So let's see what's the difference. Why do we have two formulas for hypothesis testing, and when we are supposed to use them? So if we recall, in hypothesis testing we have two different formulas for calculating sample size. And why this is so? Because we have one formula for the single-tailed hypothesis testing and another for two-tailed hypothesis testing. So let's see what a single-tailed hypothesis testing is and what's a two-tailed hypothesis testing. Okay, so we'll start off by revising some of the basic concepts in hypothesis testing. So basically we have a hypothesis. So a hypothesis is a statement of belief used in the evaluation of population parameters such as the mean of a population, mu. Okay, so we have two kinds of hypotheses in hypothesis testing. One is the null hypothesis and the second one is the alternative hypothesis. So first one is the null hypothesis. So a null hypothesis is a claim that there is no difference between the population parameter and the hypothesized value. So basically we'll state that either the null hypothesis states that mu is equal to mu naught. Mu naught is something which is already established and is a known fact. So the null hypothesis will always go with what's already established. So it will state that h naught states that mu is equal to mu naught, or h naught states that mu is greater to or equal to mu naught, or h naught states that mu is lesser than or equal to mu naught. So then we'll have alternative hypothesis. So alternative hypothesis is what a study is suggesting and what's different from what's already established. So a claim that disagrees with the null hypothesis, there can be three such claims. So mean of a population mu does not equal the hypothesized value mu naught. So basically it has to counter this claim. So it states that it is equal to, and this claim says it is not equal to. So this is called a two-tailed hypothesis testing. So basically we are dealing with both the sides of the hypothesis testing. So basically even if mu is greater, still it is rejected. Even if mu is smaller, still the null hypothesis is rejected, because null hypothesis states that mu is equal to mu naught. So even if it's greater or smaller, doesn't matter, it gets rejected. On the other hand, for these kinds of null hypothesis, we have these kind of alternative hypothesis. So mean of population mu is lesser than the hypothesized value mu naught. In symbols, alternative hypothesis states that mu is lesser than mu naught. So this is a single-tailed hypothesis testing, because if mu is greater than mu naught, this alternative hypothesis is having no significance and the null hypothesis isn't rejected. But if mu is smaller, only then it gets rejected. If it's greater, it is not rejected. So only one side of the tail is involved, as compared to the other test where we had both the sides of the tail involved, because even if the mu is greater or smaller, in both the cases the null hypothesis gets rejected, because null hypothesis states that mu is equal to mu naught. So that's the difference between a single-tailed and a two-tailed hypothesis testing. So moving back to our topic. So here we saw that we have two formulas, this one and then we have another formula over here. So what's the difference? So the difference is that over here we have this formula which is specific for single-tailed hypothesis testing, whereas this formula will be used for not for single tailed. Here is a typo. It will be used for two-tailed hypothesis testing. So let's see. We have this formula. So let's see what each of the variables stands for. N is the sample size that we have to calculate in case of single-tailed hypothesis testing. So we have already discussed what's the difference between a single-tailed and two-tailed hypothesis testing. So N is the sample size that we need to calculate. So sigma is the standard deviation. We have already discussed if the standard deviation isn't given, we can simply divide the value of range by 4 and we get the value of standard deviation if range is given in the question. So if the question states range, we'll divide it by 4. If the question states standard deviation, we'll directly use it over here. Okay. So then we have the values z alpha plus z beta whole square divided by delta square. So what's z alpha? So z alpha, it is calculated by looking up the value of probability of 0.5 minus type 1 error in the z table and finding the corresponding z value. Okay, so we'll see how it is done. Then we have the value of z beta. It is calculated by looking up the value of the probability of 0.5 minus type 2 error in the z table and finding the corresponding z values. Okay, so before we go on, we first must see what are the type 1 and type 2 errors, so we actually know what we are dealing with. Okay, so basically in inferential statistics we have two types of error, type 1 and type 2 error. So what's type 1 error? Type 1 error is committed if we reject the null hypothesis when it is true. So if we reject the null hypothesis even when it's true, this means that we are committing the type 1 error. So the probability of committing the type 1 error is denoted by alpha, and which means if we reject the null hypothesis once it's true, even though it's true. Okay, so what's type 2 error? Type 2 error is committed if we fail to reject the null hypothesis when it is false. So here we rejected the null hypothesis when it was true, and here we failed to reject the null hypothesis when it was false. In both the cases the situation should have been opposite. That's why these are called errors. So and this type 2 error's probability is represented by beta. Okay, so once the question talks about type 1 error, we know that this is the probability that we reject the null hypothesis when it is true. Type 2 error is the probability basically that we don't reject the null hypothesis when it is false. Though actually if it wasn't for the error, it should have been type 2 error is committed. Type 2 error is committed when we fail to reject the null hypothesis when it is false. So basically what we should have done ideally is we should have rejected it once it was false, and we should have accepted it once it holds true, but we did otherwise. Okay, so then we have these two things, power of the test. So basically if we subtract 1 minus p, so power basically is denoted by this formula. So power is 1 minus beta. So beta is the probability of type 2 error. So let's see how we'll work this one out. So here is a brief summary of what the type 1 error and type 2 errors are. So basically here we have the null hypothesis being true, and here is the null hypothesis false. So this is the actual situation, but what the investigator or the researcher does is rejects null hypothesis in this case and fails to reject null hypothesis in this case. So basically when null hypothesis was true but the scientist or the researcher rejected it, he or she committed a type 1 error, which is represented by alpha. Okay, and when null hypothesis was false but the researcher failed to reject null hypothesis, then he or she committed type 2 error, which is denoted by beta. Okay, so if we subtract beta from 1, we get what's called the power, and if we subtract alpha from 1, we get what's called the confidence. So this is a brief summary, a brief overview of the types of errors that we can commit. Okay, so I'm going back. So Z alpha, it is calculated by looking up the value of the probability of 0.5 minus type 1 error in the Z table. So we have a table called the Z table, and it looks like this. Here's the Z table. And then moving back, and Z beta, it is calculated by looking up the value of the probability of 0.5 minus type 2 error in the Z table and finding out the corresponding Z value. Okay, so now we know how n, which is the sample size, works. We know what's the standard deviation, how we calculate it, or we actually find its value in the question. Then what's Z alpha and what's Z beta, we'll go on to see how we actually calculate their values. Once we look at the examples, then we take a whole square and then we divide by delta square. So what's delta? Okay, so delta, it is the difference between the null hypothesis and the alternative hypothesis we wish to detect. Okay, remember that in hypothesis testing we wish to reject the null hypothesis when it differs from the alternative hypothesis. However, it is our choice that how much small difference we wish to detect, that is how much precise we want to be. Okay, so let's see an example and then we'll be much more clear on this topic. So remember that we are actually doing hypothesis testing, which is a single-tailed hypothesis, which is a single-tailed hypothesis testing, and then we'll move on to two-tailed hypothesis testing. But for now, we are only doing single-tailed hypothesis testing. So this is the formula for single-tailed hypothesis testing. Let's see. Okay, so this is an example over here. A serial packager is concerned that one of their machines has a mean fill per package of more than 16 ounce. The labeled net weight. While this is not bad from a public relations standpoint, it could cost the packager a great deal of money. So a great deal of cereal is being wasted, and the manager of that company, he or she is concerned that we actually need to save this product from being wasted, or a single consumer getting more than what he or she is paying for. So previous experience suggests that the standard deviation of the package fill weights is approximately 0.225. Okay, so for testing, so the null hypothesis states that mu is equal to 16, but the manager of that company or the CEO, he or she is concerned that mu is actually greater than 16. So if mu is smaller than 16, it is completely fine because their product isn't being wasted. But if mu is greater than 16, then it is something they need to worry about, because their product is going to waste for a single consumer who he or she is not paying for but is actually getting much more. So we'll have to counter that. So h naught is mu is equal to 16, h alternative is mu is greater than 16. So with alpha is equal to 0.05, so they have given us the value of type 1 error, which is alpha. Determine the sample size required to make beta is equal to 0.01 or less if the actual mean is 16.1 ounce or more, by putting this restriction on beta. The packager is saying that she wants a very small probability of falsely rejecting the null hypothesis, mu is equal to 16, when in fact the actual mean is 16.1 ounce or more. Okay, so how we'll calculate it? We have this formula, and here we have the sample standard deviation. So standard deviation is given in the question and it's equal to 0.225. So we take a square of that. Then we have to plug in the values of Z alpha and Z beta. So let's see. Okay, so we plugged in the value for the standard deviation, which is 0.225, and which was given exactly in the same way in the question. So in the question we had this value over here. Standard deviation of the package fills weights is approximately 0.225, so we plugged in this value. Now it's a bit more complex for other things, so we have to plug in the value of Z alpha plus Z beta over here. This is Z alpha and this is Z beta. So how do we calculate the values for Z alpha and Z beta? So let's see. So the value for Z alpha So we have alpha is 0.05 and beta is 0.01. So first we'll calculate this value of z alpha using alpha is equal to 0.05, and then we'll use the value of beta by using beta is equal to 0.01. So let's see how we calculate the value for alpha is equal to 0.05, how we calculate z alpha over here. So basically what we'll do is we have the value of 0.05 for alpha. So how we calculate the value of z for z alpha? Let's see. Okay, so you'll start on by subtracting 0.05 from 0.5, and this comes out to be 0.45. Okay, so we'll start with subtracting 0.05 from 0.5, and this comes out to be 0.45. So now what we have to do, we'll use this value and we'll look it up in the z table. So here is the z table. So how do we use the z table? So basically we'll search this value in here in all this area, and then we'll see the corresponding z value. So basically the first decimal or the first part of the z values comes off from here, and the second decimal place is followed through here. So let's see how this happens. So we'll have to look for 0.45. So let's see 0.4, 0.4, 0.4, 0.4, 0.4, 0.42, 0.44, 0.44, 4.95, 0.405. So this is quite close. So basically people, they use accurate online available or basically computer softwares to calculate the z values, but here we have this table which is a conventional method. So we'll see 0.45, which is over here somewhere. So basically what we'll do is we'll use this arrow, and then we'll see the corresponding value is 1.6. Then we'll hold this up. Where did it go? Okay, so okay, so here we have 1.6, and then we have 5. So the value is 1.65. Z value for z alpha, which is 0.05, comes out to be 1.6, 1.6, which corresponds to 0.45 is 1.6, and then we have 0.05. So just adding them together, 1.65. So let's go back and see if we have calculated correctly. Yes, we have calculated correctly. The value is 1.65. So likewise we'll have to calculate the value for z beta. So let's see how we can do that. Okay, so let's see how we'll calculate the z value for z beta. So the process is similar. So let's see what's the value for beta, 0.01. So what we'll have to do, first of all, always remember that first we'll have to subtract this value from 0.5. So 0.5 is, we'll have to subtract 0.01 from 0.5, and we have, what do we have? 0.49. Oh, here we have 0.49. So now we'll go on to the z table to look up for this value. Here we are. So this is the place where we search. So 0.49, this one is the most nearest value over here. So 0.49. So we'll use this arrow. comes out to be on 2.3, and then we'll use another arrow to see the column where we stand. So the column is 0.03. So here we are, 2.3 plus 0.03, which comes out to be 2.33. Let's see, have we calculated this z value correctly? And yes, we have 2.33. So z beta is 2.33. So this is how we calculate z alpha and z beta. So we'll add both of them and then take a square. Then we'll have to divide by what? Delta. So how do we calculate delta? Just go back over here. So delta is the difference between the null hypothesis and the alternative hypothesis that we wish to detect. So let's see. They say that the null hypothesis is mu is equal to 16, while they are claiming that in fact the actual mean is 16.1, which comes out to be the alternative hypothesis. So we'll subtract 16.1. We'll subtract 16 from 16.1, and the difference is 0.1, and here we have the value of delta. So it's simple. So we'll have to plug in those values a bit. We'll have to realize that z alpha and z beta are to be calculated individually. Do not forget to subtract 0.05 from 0.5 before you look it up in the z table. Okay, so here we have the value 79.99. Always remember, we round it off to the next figure, and here we have a final sample size, which is 80. That is, the Baxter must obtain a random sample of n is equal to 80 cartons to conduct this test under specified conditions. So alhamdulillah, we have understood how we calculate sample size for a single-sided or single-tailed hypothesis testing. Now we'll move on to calculation of sample size for two-tailed hypothesis testing. So let's see how this works. So basically we have a similar formula as we had in the previous case. We have everything similar. We have the square for sigma, standard deviation. We have square for delta square. We have z alpha by 2 and z beta and whole square. So the only difference is that over here, because it's a two-tailed hypothesis testing, we'll be dividing alpha by 2, whereas in the previous case we weren't doing so. So in over here the formula is altogether similar, except for the fact that alpha remains the same, but over there we'll have to divide alpha by 2 before subtracting it from 0.05. So n is the sample size, sigma is standard deviation. If standard deviation isn't given directly, we'll divide range by 4 and we'll get the standard deviation. Okay, so z alpha by 2 and z beta. So in the previous question we were calculating z alpha and z beta. Over here we'll only have a slight difference, and we'll be calculating z alpha by 2 instead of z alpha. So it is calculated by the steps described above. Okay, so z alpha by 2, how it is calculated we'll see, and z beta I've already shown you. So z alpha by 2, if you recall, we already had this thing previously as well. So and then we'll have to divide by delta. It is the difference between the null hypothesis and the alternate hypothesis that we wish to detect. Okay, so example 6, which happens to be the last example of this topic. So let's do it quickly and let's get done with this. Okay, so here we have our example. Suppose you want to test the claim that the average birth weights of children born to non-smoking women in Pakistan is 3 kg. Assume the standard deviation of birth weights is 0.5 kg. Find the required sample size in order to be able to detect a difference of 0.2. So this is the value of delta with at least 90% power and at 0.05 level of significance. So level of significance is a term used to refer to alpha, and we obviously remember that alpha is the type 1 error, the probability of the type 1 error happening. Then we have the power. So power is 1 minus beta. If you recall, power is 1 minus beta, and beta is the type 2 error's probability. So basically in the question they haven't given us alpha and beta directly. Instead what they have tried to do is they have actually tried to confuse us using these terms, power and level of significance. So obviously you'll have to remember that level of significance is the same thing as alpha, and alpha is the same thing as the type 1 error happening, the probability of the type 1 error happening. And power is given by the formula power is equal to 1 minus beta, and beta is the type 2 error. Okay, so let's see. Alpha is 0.05, beta is, so what we'll do, we'll subtract power from 1. So basically what we'll do over here is we'll have to rearrange this formula. So beta is shifted over here, so it becomes positive. Beta is equal to 1, and then we'll shift power over here, so it becomes negative. So beta is equal to 1 minus power. So if we rearrange beta, which is the probability of type 2 error happening, is equal to power 1 minus power. So this is the new formula. So then what we'll do, we'll calculate beta by using 1 minus power. The value of power is 90%, so we'll definitely have to convert it into simple numerical form, which comes out to be 0.9, because how we convert it, we divide 90% by 100, because percent, which is 100, so 90 divided by 100, it comes out to be 0.9. So beta is equal to 0.1. So this is how we calculate beta. Alpha is given in the question, which is 0.05. Okay, so let's move on. We have this question. So n is equal to, here we'll have to put in the value of standard deviation, which is 0.5 given in the question. Then we'll have to put in the value of delta, which is 0.2, already given in the question. Then we'll have to put in the value of z alpha by 2 and z beta. So I've already shown you how we calculate z beta. Obviously we do not need to go into that detail. So if we look up the value of z beta, how we'll do that, we'll actually first subtract the value of beta from 0.5. So here it is 0.1, which comes out to be 0.4. Then we'll look this value in the z table, and then we'll look this 0.4 in the z table. And if we go to the z table and try to look for 0.4, here we have it, the value nearest to 0.4015, and then we'll see that over here we have 1.2, and then in this column we have 9, so the value is 1.29. So if we say over here it's 1.2, it's 28, quite close to that. Okay, so once we are calculating the z value manually, we can actually go with this. Then z alpha by 2, so this is quite simple, because we'll definitely discuss it after this, how we calculate z alpha by 2. I've promised you from the beginning of this session that we'll discuss it. Okay, so just plug in the values. Z beta is 1.28 or 1.29, doesn't matter, because we are actually calculating manually, so it can be a bit different. Then 0.5, which is the standard deviation, 0.2, which is the difference, and then z alpha by 2, how it is calculated we'll discuss, and then the value is 65.61. so therefore in this case a sample size of at least 66 is required. So that's it. So before we end this session, we'll definitely discuss how Z alpha by 2 is calculated. So it's given over here. We'll go through each step one by one. Inshallah, it will be clear. So how do we calculate Z alpha by 2? I promised you in the beginning that I'll show you how we calculate Z alpha by 2, and here we are going to discuss how it is calculated. So first we calculate it using the following steps. Look at the value of level of confidence given in the question in the form of percentage, example 95%. So let's see, like over here we have been given with a level of confidence of 95%. What next? Convert that value into alpha. So how do we convert the level of confidence into alpha? So alpha, just as a side note, is also the probability of type 1 error happening, and also it is called the level of significance, not level of confidence. Level of confidence is this thing. Alpha is also called level of significance. Okay, so convert that value into alpha by subtracting it from 100, which becomes equal to 5%. Okay, so now convert this value into a numerical value because it's obviously a percentage over here. So 5%, how do we convert it into a numerical simple value? So we divide by 100 because 5%. So percent is 100, so 5 divided by 100. So which comes out to be 0.05. So this 0.05 that we got is called alpha. To get the value of alpha by 2, divide the alpha by 2. So 0.05 is obviously divided by 2, which comes out to be 0.025. Okay, so now subtract the answer of the last step from 0.5. So 0.5 minus 0.025, which comes out to be 0.475. Now we'll use a Z table to find out the corresponding Z value. Okay, 0.475. So we'll look at the Z table to find out the corresponding Z value. So where is the Z table? So 0.475 is here. If you look over here, we have 1.9. If you look above, we have 0.06. So 1.96. So obviously we were using this value for 95% confidence. Whenever we encounter 95% confidence, we use the value 1.96. Over here we use 1.96 because we had 95% confidence interval. Over here we had 95% confidence interval and we used the value of 1.96. Even in the last question that we discussed, Z alpha by 2 was 1.96. Why? Because we had 0.05 level of significance. So if you recall, 95% confidence interval is equal to 5% level of significance, because level of significance is found out by subtracting it the level of confidence from 100, which if it's 95% confidence, then 5% level of significance, and 5% level of significance is 0.05. So it's the same thing, and that's why we have 1.96 as our answer. So if you remember these steps, how to calculate Z alpha by 2, you can calculate Z alpha by 2 in all circumstances whatsoever, inshallah. So that's it. So we have discussed what we have discussed over here. We have discussed sample size calculation for both for estimation and hypothesis testing, and in hypothesis testing we discussed how to calculate sample size if it's a two-tailed hypothesis testing or it's a one-tailed hypothesis testing. Now how do we see if it's a two-tailed hypothesis testing or a one-tailed hypothesis testing? So this formula is for a single-tailed or one-tailed hypothesis testing, and here we had to use it because the manufacturer was concerned about only one side of the tail, which was more, because she had nothing to do with less amount of product going to her customer, though it has a negative impact, but she was worried that more amount of product is going to a customer, more than what they actually state on their packages, and that was causing them a huge load of loss. So but over here in this example we used two-tailed hypothesis testing. So basically what we were testing is that suppose you want to test the claim that average birth weights of children born to non-smoking women in Pakistan is 3 kg. So basically we are testing this claim. This claim is made by the government of Pakistan, that average birth weight is 3 kg for non-smoking women, their children. So basically why this is a two-tailed hypothesis testing. So if the average birth weight is lesser than 3 kg, then the null hypothesis gets rejected. If the average birth weight is greater than 3 kg, we are also rejecting the null hypothesis in that case. But in the previous example, we weren't rejecting the null hypothesis if it was lesser than 16 ounce. So basically we were dealing only with one side of the tail over here, but over here we are rejecting it in both cases. So that's why this is a two-tailed hypothesis testing and this is a one-tailed hypothesis testing. So if you want to go into the detail of what's a two-tailed and a one-tailed hypothesis testing, you can either Google or refer to CHSME part 1. That's it. Thank you very much.